of course, spin is, as you know, undergraduate physics, spin is not dimensionless, right? Spin is angular momentum, therefore the fundamental unit is h bar, but we make it 1, right? So those are reminders, and there's another one coming later, but let's go on. Okay, another thing. According to this historical way of writing exchange Hamiltonian, when J is positive, then you're dealing with the ferromagnetic interaction. By that we mean two magnetic dipole moments want to be parallel to each other, right? When they're parallel to each other because of negative sign, energy is lower. When they're anti-parallel to each other, then of course this is negative when you have a negative, so the energy is higher. On the other hand, if the J is negative, you're dealing with a system in which magnetic dipole moments want to be anti-parallel to each other, right? Because of the negative sign, okay? But this is sometimes inconvenient because, as it turns out, I may not have time to explain it to you in these two lectures. As it turns out, the ferromagnets are almost completely understood. It's not very interesting anymore. Ferromagnetic materials are very important in some applications, or ferromagnetic metals are very interesting. If you inject electrons from ferromagnetic metals to non-ferromagnetic metals, then electrons have magnetic moments, which are not random. And you can apply magnetic field and make preferentially electrons with magnetic dipole moment pointing only one way tunnel into or go into normal metals. And this is one of the methods used in so-called spintronics. So in application-related areas, ferromagnets are still important, but from fundamental point of view, antiferromagnetics are almost completely understood. So people nowadays those people who study magnetism are focusing on antiferromagnets. So for that reason, often people write the Hamiltonian this way. No minus sign. Okay? And also they drop this 2 because you have a factor 2 for a historical reason. So often you see a Hamiltonian like this, but now this is very inconvenient because negative sign or positive sign, it's okay. Somebody say, okay, J is 5 degrees, but they're dealing with an antiferromagnet, then you know in this old language it's minus 5 degrees. But there could be a factor 2 difference. Okay? And the problem is often people don't write down which Hamiltonian they're using because everybody knows the Hamiltonian, but the problem is that there's a factor 2 difference between different people. So if you read some paper and they say that, okay, the paper says that the interaction is 2 degrees, then you have to be very careful whether they mean 2 degrees in this way or 2 degrees in this case, because then the interaction between neighboring pairs is different by factor 2. Okay? So this is the 5th point. So I think that covers almost everything, every subtle points I wanted to point out. So let's go on to do the mean field approximation. Now we're just going to rewrite this Hamiltonian with no approximation at this point. Of course, you can write if only the nearest neighbor magnetic dipole moments interact with each other. Okay? So let's restrict ourselves to nearest neighbor case. And furthermore, we assume that interactions are isotropic. All the neighbors interact with exactly the same strength. This is not always the case, but make it the same to make the situation as simple as possible. So J is isotropic. Right? If so, J is a constant, therefore it comes outside, minus 2J. And we're going to take a sum of I and J separately. So I runs from 1 through n, where the number of particles is n. S sub I. Then you take the sum over j separately, but only the nearest neighbors. All right? Now, if you did so, you'd be double counting, right? Because let's say you have a very simple lattice in which magnetic dipole moments make either cubic or square lattice. I can draw a three-dimensional structure very easily, so read this to be either two-dimensional square lattice or three-dimensional cubic lattice. And if I call this height I, then nearest neighbors are here, there, there, there. But when I call this one I, then nearest neighbors are here, cross, 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 right? So this pair, I have counted twice, right? So to take care of that, you have to drop to here. Okay? Then this Hamiltonian is exactly the same as this one, right? You're not doing the double counting. Got it? So far, there's no approximation. The only thing is that we are considering a case in which the j does not depend on which neighbor you're talking about, and the interactions are only between nearest neighbors, right? So if you look at this one, let's say this spin, which is located here, spin. By spin, we mean the magnetic dipole moment, interact with 4 nearest neighbors if the ions are arranged on a square lattice. Okay? Am I speaking slowly now? Slightly better? Still too fast? Okay, if you think I'm still talking too fast, raise your hands. Okay. Okay, I'm going to slow down even more. All right? And write down what I say as much as possible. Okay, so now we're going to do a mean field approximation, which many of you know already. Okay. In the mean field approximation, you replace this with the average value. And of course, the average value should not depend, in many cases, on which ionic site you're talking about. Particularly in a case like square lattice or cubic lattice, all the ions are the same. In a sense, there's no special position. Okay? Therefore, the average should be the same for all the spins, all the magnetic dipole moments. So you replace each of these ones with the average value. And if the number of neighbors is z, nearest neighbors, let's say if you have a square lattice, then you have 1 above, 1 below, 1 to the left, 1 to the right. There are 4 nearest neighbors, right? You have a cubic lattice, then you have 2 in one plus x direction, minus x direction, plus y direction, minus y direction, plus z direction, minus z direction. There are 6 neighbors, right? So z is the number of nearest neighbors. Some people call this number the configuration number. Okay? So you have replaced the actual sum of the neighboring spins by the average spin value times the number of such neighbors. This is the mean field approximation in magnetism. Okay? What you're doing is that you replace one of the operators in a Hamiltonian with its average value. That's basically mean field approximation is in general. If you did so, since this is average value, it comes outside. C times J times S times S sub R. Okay?